Hello everyone, welcome to topic 5.5 collision model. By the end of this, you should be able to explain the relationship between the rate of an elementary reaction and the frequency, energy, and orientation of molecular collisions. So we're going to dive into what is collision theory and how does this explain the requirements for a successful reaction. So the collision theory explains why different reactions occur at different rates. Particles collide all the time, but not every collision results in a reaction. A reaction occurs when bonds are broken and remade. So you have to have specific conditions met in order to break and make those bonds. Collision theory then states that in order for a reaction to take place, the following must occur. First, particles must collide, right? If they don't touch each other, there's no reaction that's going to happen. They must have sufficient energy. We call this activation energy, EA, E sub A, and it corresponds to the amount of energy needed to break the prerequisite bonds. So it has to hit hard enough to break the bonds. The particles must be in the correct orientation, so they have to be pointing the correct way and collide in exactly the correct way for a reaction to occur. So honestly, reactions really aren't super common because there's a lot of requirements for them to actually occur. So looking at collisions occur all the time, but not all collisions result in a reaction. When we think of reactions in terms of collisions that need to occur, it helps to explain why a bimolecular reaction can occur, because the chance of two molecules colliding is pretty high, but why a termolecular or higher reaction is unlikely to occur, as three particles colliding at the same time is much more unlikely. Like a statistical whatever business, it's more likely that you can have two hit in just the right way than to have three orient themselves, like a three-legged foot race, and actually make that work, right? Trying to, like, two-legged foot race is kind of like pushing it, but it can happen. Trying to do it for three, it's going to take a lot of talent on somebody's part, and somebody's probably running backwards because you have to be in just the right orientation for the reaction to go. So in order to increase the number of collisions, you must increase the concentration of the particles. If your reactants are solids or immiscible liquids, then increasing the surface area, so the amount of particles that are available to be reacted with and thus collide, will increase the rate of the reaction. Now looking at activation energy, which is the minimum amount of energy that the reacting particles need in order to react. If the colliding particles don't meet a minimum energy threshold, so they don't have energy equal to or greater than the activation energy, then the particles will simply bounce off one another without a reaction taking place. The energy is used to break bonds. You have to have enough energy available to break the bonds. In 3.5, the Maxwell-Boltzmann distribution curve was introduced. It's shown here below. We saw that the temperature is a measure of the average kinetic energy of the particles. Some particles move more quickly than others, and so we see a distribution of that. On this graph, we can plot the activation energy, EA. And so what that tells us is that everything above that activation energy, so at and above, has enough energy to actually react. However, anything that is below that, so all of these, do not have enough energy to react. So there is no reaction that's going to happen with anything that does not meet that activation energy threshold. Okay? So in order to increase the number of particles with great energy greater than the activation energy, you have to heat the sample, right? The average kinetic energy must increase, and that is temperature. So you must increase your temperature. A general rule is that for reactions which are relatively slow at room temperature, increasing the temperature by just 10 degrees Celsius will result in a doubling of the reaction rate in general. The rate increases because more particles have energy greater than the activation energy. It's a common misconception that the reaction is faster because the particles are moving faster, this only accounts for a small increase. So what they're getting at here is because they're moving faster, they're colliding more frequently. And yes, that does increase the chance of a successful collision. But the out of the two, like colliding more frequently versus colliding with enough energy, the colliding with enough energy produces statistically more successful collisions by increasing the temperature, not just the frequent collisions. Okay. It does help a little, but not significantly. So you can see here that by increasing the temperature, we increase the amount of particles that have an energy equal to or higher than the activation energy. So please note that heating a sample changes the amount of particles that have the activation energy or are greater than, so meet that threshold or surpass it. It does not change what the activation energy is. That is always set and constant because those bonds are not changing, like the bonds that you need to break and the bonds that you need to make. Those do not change. You can change the temperature, which changes the number of particles that can break and make bonds. Finally, orientation is also key. So specific parts of one particle must collide with specific parts of another particle in order for a successful collision to occur. So that means a reaction happens. This is described as their orientations, right? So if you're trying to give somebody a high five, you guys kind of have to be pointing the right direction in order for that high five to be successful. The reaction shown to the right is given in this equation. If you look at the possibilities for the reaction on the right, only one orientation, not that one, I can't, that's not right. This one is the only one where we have it oriented correctly, right? So because of the orientation, that is the only one that'll actually work. The others are not pointing in the right way, and so they are not going to be able to break the specific bond that needs to be broken and then make bonds, because in this case it's multiple, and then make the bonds that result because of that. So looking at some practice problems, given the following reaction, which set of reaction conditions will result in the highest reaction rate? Explain in terms of collision theory. So we're going to look at this, and it's going to have to be something that first has more chances of collision, has enough, the correct temperature or enough energy, and has an orientation. Well, looking at the data, we don't have an orientation aspect. So that third one that we talked about is not going to factor in here. Also, the temperature is the same for all of them, so temperature isn't going to. So we need to look at which one is going to result in the most collisions. Okay, so when we look at this, we see, oh, this one has more particles, but we then compare here, and this has 4 times as much space. So if we move from, like we're running around the classroom, and we move from the classroom then to the gym, even if we doubled the kids in class, right? The gym is like 4 times the size of the classroom, maybe a little bit more. But if we move to the gym and had you guys all run around, you're less likely to collide with other people than, say, if you were in the classroom, even if you doubled. Okay, so these two were looking at, So it can't be experiment 2 because even though you double the concentrations, you quadruple the volume of the container. So they're going to collide less frequently. Then we now can compare 1 and 3. And we see they have the same number of particles, but there's more space in the first experiment. So more space means fewer collisions. So our answer has to be experiment 3. And you can say something to the tune of concentration of particles is highest, thus will collide more, and the rate increases. So concentration. Okay. So looking at the the graph below shows a Maxwell-Boltzmann distribution for the reaction at 3 different temperatures. On the first graph, add a line to represent a very low activation energy, right? And remember, speed is like kinetic energy. So if we're going to draw a line that represents that, this would be a low activation energy. So E, low activation energy. On the second graph, we're going to add one that has a very high activation energy. And we could even just be kind of extreme and say, hey, here's that very high activation energy. Explain why you don't see a large increase to the reaction rate when temperature is increased if the activation energy is low, right? So if I increase the temperature, that causes all of these, and we see that with the red to the blue to the green lines, causes the graph to spread out. And we do see that the area under this curve, that of all the ones that are not eligible, like decreases a little bit, but it's not statistically significant to all the ones that are able to react. Like the ones that are able to react are the vast majority of the sample because of the low activation energy. Heating it is not going to produce a significant temperature change. However, if we looked at the last one, as we increased the temperature, we actually had some that were then able to react. So here, for the one, when we have a low activation energy, we could say that there are already a lot of particles that meet the minimum. So changing T doesn't increase the minimum number of particles with enough energy significantly, right? So now with that, you are going to work on the UDOs, check your work, and thank you for tuning in.